All right, so we're going to spend a few minutes at the beginning of class. I'm going to show you what a good example submission looks like for phase one. It's a student from 2 years ago who just did a really nice job, like with their logic, their calculations looked nice. I'll tell you all the things I like about their submission just so that you can be on track for March 14th. That's when you need to submit your summary table, your hand calculations, and then the write-up summary describing your method, data sources, and so on. Homework 8 is due on Monday, March 24th. I've loaded that to Blackboard. It should be visible to you now. So that's just the day after spring break. So I guess you're spending spring break working on homework number 8. Actually, you could probably do most of it after what we're going to go over this week. So today we're going to continue talking about some ideas from Chapter 11, which is steady uniform flow. But let's talk about the project. And remember, in the project, what you're doing is demand estimation. We have some hypothetical development that is going to be built, and you're trying to assess how much water is needed at each of these green arrows. So you're going through a logical analysis process of trying to determine things like how big is the north zone? How many people live in the north zone? How much water is each person going to use? How does that water demand vary over time? So this is this student from a couple years ago was assigned Minneapolis. And so this is a single continuous PDF that has all of their, it's got the summary table, it's got the hand calculations, and the PDF report, and that's great. There's a variety of websites where you can join PDFs together, so it's a single continuous file. But if you want to submit one which is your scanned work and then one which is a PDF output of your report so that it's two different files, that's also acceptable. But here they've got all of their flow rates organized very clearly. You can see the effect of, for example, going from the average daily flow to the peak day. And you may remember that the factor that I told you is that the peak day should be 1.8 times the average day flow rate. And then the peak hourly flow rate is 3.25 times the average day. And so the design flow would be the larger of either the peak flow for the hour or the peak day plus the fire flow. So here it's got the 72.1 is the peak day plus fire. The peak hour is 76. And so the residential demand that we're going to use for the north zone would be the larger of the two. And then they also had the commercial demand. Do you remember what I said, like what kind of things cause the commercial demand? Like what does it represent? What does commercial mean? Yeah.
That was just like you'd have like malls and just attractions.
Okay.
Attraction based.
That's partly it. It's people not at home. So it could be people in a shopping center. But we do have a separate shopping area here in the east zone. So what I'd like you to do for the north zone is assume that it's people at work, like office parks. So people in an employment scenario. And so how much water are they going to use there? It's different because you don't do your laundry at work. Generally, you don't take a shower at work. Although I have showered at work. I've showered down the hall. There's a shower in the single occupant restroom down at the end of the hall. But not very often. So anyways, water demand is different at home than it is at work. So they've gone through this process, and it's probably not necessary for them to be reporting the demands to the nearest, what is this, thousandth of a liter per second. Probably it'd be okay to say 23.4 liters per second. Doesn't need to say 23.433. But I mean, I'm just splitting hairs at this point. It's a good submission. So the total design flow is the sum of all of the design flows for the north zone plus the design flow for the south zone plus the design flow for the east, and then all of the external flows contribute to the total design flow. But really, we want to know how much water is needed at each of those green arrows. And once you've got values on this table, then you're able in phase 2 of the project to start using water gems to figure out how big the pipe needs to be. So what I liked is that it was really logical. The calculations were done in the order that they are reported on the summary table. So that's good. Like if the calculations start with the box factory and then go to the commercial demand of the North Zone and then the hotel, like what would be the point of doing your calculations in a disorganized way that's different from what is summarized on the first page? So I like the fact that, we're starting with the North Zone, and what's the most logical thing to do on the North Zone is to determine how big it is. And so they've used the scale map which is provided to figure out the area. They've used their assigned population density to find out the total population that's in the North Zone. Then they told me according to reference 1, and later on in their report I can get more details about reference 1, but they found some specific details related to water demand in Minneapolis, different from the national demand. So there's 2 main ways that you can improve on the data that I provided as an example. Remember, there's a PDF file online that's from like the early 1980s, and it has some nationwide averages on what the average person in the United States, what their demand for water was in the 1980s. And so the 2 main ways that you can improve on that provided data. Now you can use that provided data if you're just kind of aiming to complete the project but don't want to distinguish yourself in any way. But if you just do a little bit more research on like what are flow demands today, not in the 40-year ago range, and then also what are some more geographically applicable demands. So, I've said before, if this person wasn't able to find data for Minneapolis, maybe they could have found it for St. Paul, which is just right across the river. Or if you can't find it for Minneapolis or St. Paul, well, Chicago's pretty nearby. Probably the Chicago water demands, it's a city in the Midwest, northern latitude, temperate, well, not temperate climate, but similar climate. It's going to be more applicable than a nationwide average. So this person did find some locally applicable and relatively recent flow demand data. And so then they determine the per capita demand and converting between the units in a really clear way. Gallons per day. Now we're going to make it liters per day. So I never had, even though the handwriting can be improved a little bit, that's okay. It's still logical. It's organized. They're not trying to cram too much onto a single page. I've given you some free paper, so you can just, let your hand calculations breathe a little bit. Don't cram it together and make it hard to read just to save half a penny on paper. So I like it because it's organized. It's easy to follow. I was never confused by, for example, the order that the calculations were done. They always made it clear what the assumptions were based on. It was based on a certain reference that they had found. So they go to the South Zone and start with the area, population density, total population, demand per person, demand overall, then peaking it from the average day to the maximum hour to the maximum day plus fire and so on. They had good assumptions when it came to like the shopping mall. You're going to have to, I don't want you to copy their assumptions, so I won't show it for too long, but you're going to have to think about, if you know how many stores there are at the mall, how does that translate into the amount of water that's going to be used? How much water does a store use? And I want you to just kind of logically think about, if you need to, do some research, go to the mall, ask if they've got a bathroom, look at how many toilets they've got in a bathroom for a small store versus a big store. What's the mix at a shopping mall of, if there's 60 stores at the shopping mall, are every single one of them Dillard's? No. Some of them are going to be small. Some of them maybe are little kiosks that aren't using any water at all. So just show me evidence of some logical analysis that draws the connection between the number of stores and how much water they're likely to use at some sort of a facility. So they've gone through some, I've given you more hints on the sports stadium than I used to. In the past, people we're thinking, sports stadium, let's see, they need to water the grass in the sports stadium. Well, they do, but that's not going to be like the peak demand. In a sports stadium, the peak demand is, 80,000 people flushing their toilets in the 20 minutes of halftime. And so I've given you a little bit more hints related to that. So the hand calculations were laid out in the order of the summary table. It was always clear to me what their assumptions were, and I could follow the calculations. Then here, they're just kind of explaining in words what the rationale for their assumptions, what's the design process. It's a kind of a descriptive thing, and they used here just numbers in brackets to be their citation method, and you can use that if you really like it. I think author date is also a great way of doing it. But the point is if I go back here to their list of references that they've cited, it was always clear to me like what data they were using to support a certain thing. And also look, it's not just the hyperlink. That's not an appropriate way to cite references, to just put a web link. They're actually saying, who's the owner of the website? What's the title of the page? What date was it retrieved? So there is a standardized method of citing a website that you've accessed. And I think that I've given you a link to the Purdue website, which has a pretty in-depth description of different ways to cite electronic references. So here, looks like they went and found about 10 applicable references in order to describe the flow demands in their city. So they're just talking me through, for example, in the external flows, they're saying, what they're assuming for a certain stadium and how they actually found, it looks like, some data relating to how much water is used at a stadium for a similar stadium where data was available online. So anybody have questions? I just wanted to show you a few things related to what the submission should look like for phase one. Anybody want to ask questions about it? If you've got questions, feel free to stop by my office or give me a call on Teams, or you can send me an email, and I'd be happy to chat. I think that this project is, for some of you, it may be the first time that you've been doing design from beginning to end, where the design starts with an assessment of need, and it's going through the optimization process, and it's looking at factors like cost. So I think it's exciting to get a feel for what engineers are dealing with on a regular basis, and not just designing one little element of something, but looking more globally at what the design process is, from having to guess in a lot of cases. When you don't have all the answers, you have to start sometimes design with just an assumption as a placeholder, and then later on down the road, when you've got more data about a certain part of the design, you can update your assumptions and change the design. But I hope you find this project to be useful and interesting, and I think phase one, you probably could do all of phase one in 8 hours and do a nice job. Any more than that, you're probably spending more time than is necessary. Like I'd hate for somebody to spend 40 hours on phase one. I think it can be done really well in the 8-hour range. So, any questions? Yes.
So for something like this, like if you go to like the city's website or whatever, usually they have like the officials for the different like departments or whatever.
Yeah.
If we reached out to someone like that, do you think that'd be appropriate for something like this, or?
I don't think it should be necessary. I'm not saying don't do that, but if you can't find the data already online, then just go to a different city, because they're going to be swamped. They may not get back to you quickly, and if you're hoping to get some data from them and you don't hear back quickly, then I'd hate for you to experience a delay from that. So I'm not saying you shouldn't do it, but I think it's better just to, like if you've got Denver and you can't find the data that you need, go to Lakewood, Colorado, which is a suburb of Denver. Or, if you're in Los Angeles and you can't get the data you need, go to Ontario, California. So I'd suggest, I think most of the time the data you need will already be online. Other questions? All right, so we didn't take a look at this slide in class on Wednesday. There is, of course, we've talked about how Manning's equation is used for steady, uniform flow. And Manning's equation gives us the normal depth. And it uses a friction factor N that doesn't vary with flow conditions. So F values that we used for the Darcy-Weisbach equation, they're always changing. The F value is always adapting based on the diameter of the pipe, the flow velocity, the temperature. We don't have that level of sophistication when it comes to assessing the flow of open channel conditions. And so N values are just fixed for the material. And there's a range of values for different types of materials and conditions. And one of the things our book describes is the relationship between estimating the N value and then the material of the substance that is at the bed. So if you had, for example, gravel at the bottom of a river and you knew the diameter, the median grain diameter of that gravel, you could use it to estimate the N value. And because we're a little bit pressed for time, we won't go through and apply the calculations for this example. But what you do is if you know the particle size in inches, you divide that by 12 to get the diameter of the median grain in terms of feet. Just simply put it into this formula to the 1/6 power, times it by 0.34, then that allows you to estimate the N value. So you could use this also to back calculate and see what is the assumed grain diameter for different materials types. But there is a relationship, there is some empirical way of tying these N values to like a physical reality that can be objectively measured. All right, let's do some calculations. Let's practice using trapezoidal geometry, and I really hammered home last time how important trapezoidal geometry is because so many natural and man-made channels are trapezoidal in shape. So I really want you to be comfortable and experienced in doing calculations with trapezoidal geometry and Manning's equation. Let's say that we had an asphalt channel. So asphalt gives us an N value of 0.014. It has a bottom width, lowercase b, of 3.5 meters, and then the side slopes are 2.5 to 1 h to v. Now remember, in our little formula from table 10.1, it uses the letter T to describe the side slope. So if this is saying it's 1 unit of vertical and 2.5 units of horizontal, that means T is 2.5 because what we saw from, did I bring markers? Yeah. The side slopes are described as 1 to T. So if it's saying 2.5 units of horizontal to 1 unit of vertical, that just means T is 2.5. And then we know Y, the flow depth is 1.2 meters. And so what is the flow rate here? And here's the form of the Manning's equation where we, remember originally Manning's gives you the velocity. But if we multiply velocity times the area, then that is the flow rate. So this is just Manning's equation where we are trying to find the flow rate Q. So let me pause for a moment, and you're going to have to use this formula to find out what's the area, what's the wetted perimeter, and what kind of flow rate would we see through this channel under the conditions that are described. Bed slope is 0.1%. What did I tell you about S? How do we translate percent into what you need to substitute for S? What was that, Macy? Decimal. It's a decimal. S is a decimal. So here in this problem, S is 0.001 because S is 0.1% divided by 100. So we get 0.001 for S. All right, I'm going to pause. I'd like you to calculate Q. Okay, so we need to know the area and the wetted perimeter to use Manning's equation. And I guess there's maybe a couple ways to find it. I found the area the old-fashioned way, not necessarily using this formula of B plus Ty times Y. What I did was I I looked at that trapezoid and I said, well, to me that looks like a rectangle that is 3.5 by 1.2, and then it looks like two triangles on the sides, each of which are 3 by 1.2. So I said the area is the rectangle plus the two triangles together, which form another rectangle, and the area is 7.8 meters squared. There we go. Did anybody use this formula, b plus ty times y, and did you get the same thing, 7.8? All right. So it works either way. Wetted perimeter, I did use the formula that's provided there. Remember, physically speaking, what the wetted perimeter is it is this distance. It's this length on the side plus the bottom and then the other side length. So it's the perimeter that water is in contact with the surface which is resisting flow. So the wetted perimeter here, we calculate W is 2.693, and then from that find that the P is 9.962. So here I did the area the old-fashioned way and also the wetted perimeter the old-fashioned way, where I was saying, you know, that's the bottom length of 3.5 meters, and then I said, well, how much is that side length there? It's 2 of them, because there's one on the right and one on the left, times the square root of 1.2 squared and 3 squared. So I just found the length of the hypotenuse and then doubled it because there's one on either side. And that's effectively what this formula is doing as well. In calculating W and then calculating the wetted perimeter as B plus 2 times Y times W, that's doing the same thing. But did you also get for wetted perimeters 9.96 meters? All right, so then the other two parameters in Manning's equation were givens and fixed. The n value and the slope. So we should get about 15 cubic meters per second. That's how much water is passing through that channel if it's flowing at a depth of 1.2 meters on a 0.1% slope. Any questions about that? How would you find the flow velocity? Yeah, we just take this Q and divide it by the 7.8 meters squared. I should change that. It's meters squared. So the velocity is maybe just under 2 meters per second would be the flow velocity. The average velocity, there's not a single velocity. You know, there's different velocities, but the average velocity. Sometimes when we're writing the continuity equation, just to acknowledge the fact that, you know, in an open channel, the flow is moving slower at the bottom, closer to the bed material. We sometimes write V with a bar across the top of it is Q divided by area. And this means average velocity, V with the bar across it. That means, you know, across the average cross-sectional area, the flow velocity is that. Does anybody know what it means if you've got a V with a cross through the letter V? Volume. Volume. You know that. Good. All right. It's kind of weird how sometimes we reuse certain symbols. In engineering economy, you use the letter I think like 9 different ways. So, any questions about this example before we move on? Okay. Well, how many of you use the Casio calculator? Many of you use the Casio. It's, you know, what you end up learning in 111, so it's natural that you would. It's tricky, but you can use the Casio to solve Manning's equation. But it's going to look a little bit different because you don't have some of the letters on your Casio keyboard. So for example, the letter T doesn't exist on your keyboard. The letter S doesn't exist on your keyboard. So you have to like reassign variables. And this video, which was recorded from a faculty member who used to teach at Marshall and is kind of like our go-to expert for the Casio calculator. I mean, I learned how to use the Casio the one time I taught 111 and then instantly forgot it because I prefer the HP calculator. But I wanted to show you this demo, and of course you've got a link to it where you could come back later and watch it. But it shows how you could solve for any one of these variables. And so, like for example, if you're given the flow rate Q and you wanted to find the depth, the unknown depth, then you could use the solver functionality to find the unknown depth. So let me pause the recording here so we don't have a recording within a recording. And so if you look at the geometry of these example calculation values, it's the same channel that we just did our example, where the bottom width is 3.5 and the side slope is 2.5. The channel slope is 0.1%. The roughness is 0.014. So this is just saying, what if you had a flow rate of 29? That's a known. Then how deep would the water be? So like what we just found from our calculations is that when you have a depth of 1.2, that's corresponding to a flow rate of like 15. So same channel. What if instead of 15, what if now you're starting to put 29 cubic meters per second through that channel? Then the flow depth, as he calculated, was going to be 1.66 meters. And so the nice thing about having it into a solver is that you could constantly tinker around with the values. So let's say that you knew you didn't want the water depth to be more than 1.5. So you could say, okay, well, y equals 1.5. Now solve for B. Like how wide would the channel have to be to limit the depth to 1.5 meters? So you can just search on YouTube in my channel, Solve Manning's Equation on Casio, and that video will come right up, or the link is in the notes as well if you need to watch that again. I saw maybe some of you were following along. Did you get it to work, and did it take the 20 seconds to solve it? So it seems like it's stalled, but then eventually it'll give you the answer. All right. So you will, on the exam, 100%, I promise and guarantee, you will have a problem where you have trapezoidal geometry and Manning's equation. I don't know if it'll be the midterm exam or the final exam, potentially both, but you'll need to use some sort of a solver to find the unknown depth using Manning's equation. So it would be great if you went through this video a couple times, got really comfortable with how to do this on your calculator, how to solve Manning's equation. And so not everybody has a Casio calculator. I see a TI. I don't see any HPs. They don't make them anymore. So, all right. Remember that in traditional units, we have this coefficient in front of it, 1.49, that we don't have for the SI units in Manning's equation. And if you rearrange that so that you put what's known on the right-hand side of the equation and everything that's unknown on the left-hand side of the equation, that can be an effective way to find the depth when you've got a certain roughness, a certain flow rate and slope, and you're just trying to find out what's the depth, because the unknown y would be on the left-hand side of the equation. So let me illustrate for you how to solve this channel, which has a bottom width of 15 meters, where we've got a flow rate of 145, a roughness of 0.015, slope of 0.45%. And let me start with Excel and illustrate how you could use Excel to solve this one. I think I may already have a template file for myself. If not, I'll just start from scratch. All right, I'm going to do a quick screenshot here so that I can put the problem statement into Excel. So I press the print screen button, and then when I paste, it takes the image out of the clipboard. All right. So the process is I'm going to put on one side of the equation all of the constants, and on the other side of the equation the unknowns. Okay, so here I've got N, Q, and S, And so n is 0.013, q is 175 cubic meters per second, and s is 0.0045. Okay, so I'll have the left-hand side of the equation and the right-hand side of the equation. So left-hand side and right-hand side. So right-hand side is going to be these constants here. So the right-hand side of the equation for, by the way, let me move this over. I'm going to do this for like different y values, for guesses of the y value. So different guesses of the depth in terms of meters. And by the way, I guess I could put these units here, cubic meters per second for the flow rate. N is unitless and S is unitless. Okay, so the right-hand side of Manning's equation here is N times Q divided by S to the power of 0.5. And I want to anchor those references, so I'll use the F4 button to put in the dollar sign so that when I drag it down, it's always looking at those same like header variables there. Okay, now let me guess, like what is the depth that for this channel gives us flow rate of 175? So is it a depth of 1 meter? I don't know. But what would be the left-hand side of the equation if it was 1 meter? So I'm going to do the area to the 5/3 and the wetted perimeter to the 2/3. Now to do that, I'm going to also need to define what is B and also define what is T, because B, T, and Y go into the area and wetted perimeter. So B is the bottom width, and that is 15 meters. T is the side slope of 2. Okay, so now the left-hand side of this equation, where I've just rearranged Manning's equation, is the area to the 5/3 divided by wetted perimeter to the 2/3. So let me just crop this a little bit so it's a little bit less busy. Okay. So I am going to use, here's Manning's equation. I can see like the formula for the area to the 5/3 and wetted perimeter to the 2/3. That's what I'm going to type in here. So equals parentheses B, anchor that reference, plus T, anchor the reference, times Y, whatever my guess is of Y, times Y, close parentheses, to the power of 5/3. Okay, and then, okay, to the 5/3 power, and now I'm going to divide that in the denominator. Now I'm going to write the formula for the wetted perimeter. Formula for the wetted perimeter is B, anchor the reference, plus 2 times Y times 1 plus T squared. I anchored the reference to T. Now it's to the 2 power. Close parentheses to the power of 0.5. Boy, this is getting tedious, right? And then close parentheses, and all of that is to the power of 2/3. All right. So what this is saying is, if the flow depth was 1 meter, then the flow rate would, or then the left-hand side of the equation is 0.09. So what I want is the left-hand side and the right-hand side to be equal, and they are not equal. So I just need to constantly change the left-hand side, change the y value until the difference is 0. So the difference is one minus the other. And what my goal is to find what depth is going to make it so that the difference is 0. So 1.1, does that get me closer? A little bit. 1.2, difference is getting smaller. Let's try the goal seek and see if we do data, what if analysis, goal seek. We want as our goal, the difference to be 0 by changing the depth. Go. And this is leading me to believe that I may have a mistake in my formula for the left-hand side, because I don't think a depth of 123 meters is quite right. So let me just double check here and see if maybe I've left something out. So we've got b plus t times y to the 5/3 power divided by wetted perimeter, which is b plus 2 times y times 1 plus t squared to the power 1/2. Yeah, it's not jumping out at me what the issue is.
Exponent at the end, not in parentheses.
I think you're probably right. All right, let's try goal seek again. So data, what if analysis, goal seek. Yeah, I'm glad you caught that. So our goal is we want the difference between the left-hand side and the right-hand side to be 0. And we're giving it permission to change the y value. There it is. That's what I'm looking for. 1.57 meters. Yeah. All right. So you can do the numerical solver in your calculator. You can do it in Excel. You could use Wolfram Alpha. Remember, we talked, I think, about Wolfram Alpha in a previous class, and you can go to Math Input and start typing. You can start typing the equation. What I'm not sure is if you type it in like with if you just type in the equation, whether you can define the variables. We probably don't have time for me to play around with that and see, but I mean, you could put in the known values, like so. Just type in 175 for Q, type in 15 for B, and then for Y you leave it as Y, solve for Y. But numerical solving the trapezoidal channel is pretty important. And remember that we've got all these different formulas, but the trapezoidal geometry is the one that we see really a lot of in open channel flow. So the 29 cubic meters per second is the example that we saw in that video. So that was the one where it was finding out what is the normal depth if we have that same 3.5 meter wide channel and we just put more flow through it. All right, that's it for today. I hope you have a good weekend. I'll see you on Monday. Remember that maybe the thing that's at the top of your to-do list right now is phase 1 of the project. Because homework 8, that's not due until after spring break.
Thank you so much. Oh, I dropped it.